The fourth installation in this chapter on solutions is about colligative properties. So, the colligative properties are properties of solutions that depend only on the number of solute particles and not on the nature of the solute particles. So, these properties do not exist in pure solvents, neither in pure solutes. The colligative properties are manifested by solutions only. So there are four colligative properties. We have the vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. So we will go one by one and we will start with the vapor pressure lowering. So we need to define vapor pressure first. So if we have a sealed container here with a certain solvent. So we have a pure solvent. And our solvent is volatile, meaning some of the molecules in the liquid phase can easily escape into the gas phase. Okay. So there is a certain time at which the rate at which your liquid molecules escape into the gas phase and the rate at which the gas molecules escape into or enter the liquid phase is equal. So we have a constant number of particles in the gas phase. So the pressure exerted by these particles on the surface of your solvent is what we call the vapor pressure. Okay. Now, what do you think happens to the vapor pressure if we add a solute? Now, an important condition here is that your solute particles are non-volatile, meaning they do not escape into the gas phase. However, the solute particles also interact with your solvent molecules. So the solute particles sort of pull the solvent particles close to themselves, thereby preventing some of the liquid solvent molecules to escape into the gas phase. So notice here the description, the rate of vaporization is reduced by the presence of the non-volatile solute. And because of this, when equilibrium is established, there will be fewer molecules in the gas phase. So that is why if we have a solution compared to its pure solvent, the vapor pressure of a solution is lower due to the presence of the non-volatile solute particles. Now, as a consequence of this vapor pressure lowering, we have what we call boiling point elevation. So we define boiling point as the temperature at which the vapor pressure of a certain liquid equals the atmospheric pressure. So the atmospheric pressure is defined to be 1 atm. So if the vapor pressure of water equals that of 1 atm, we say that it is boiling. So this happens at 100 degrees Celsius. Now, if we add solute to water, we know that the vapor pressure decreases. So it means that at 100 degrees Celsius, the vapor pressure of the solution hasn't reached 1 atm yet. So we need to increase the temperature further so that the vapor pressure reaches 1 atm. So that is why we have boiling point elevation. Likewise, or on the other hand, we have the freezing point depression. So for this one, if we add a solute to a pure solvent, the effect in the freezing point of the solution is that it becomes lower compared to that of the pure solvent. And then finally, we have osmotic pressure. So osmotic pressure is based on the principle of osmosis. So osmosis is the transport of water across a semi-permeable membrane. So a semi-permeable membrane only allows water to pass through and not any other substance. So for example, we have here a U-tube in the middle of which we have a semi-permeable membrane. We put water on the left arm of the U-tube and a glucose solution on the right arm. So by instinct, we know that the water will flow from left to right. So why is that? Because we have more water on the left side compared to the right side. So it's like diffusion. And it takes place because the membrane allows water to pass through it. So after some time, when equilibrium is achieved, we see that the levels of the two liquids are now different. So actually, this difference in the height of the liquids brings about the osmotic pressure. Or simply put, we define osmotic pressure to be the pressure that you need to exert on the higher fluid so that they go back to their original levels. So basically, it's the pressure you need to prevent osmosis. So that is osmotic pressure. So there are several applications of osmosis. One is in your kidneys. So your kidneys filter the wastes from your blood via osmosis. Okay, and then another application would be dialysis. So for patients with kidney failures or with non-functional kidneys, they undergo dialysis to clean their blood. So the principle operating here is also osmosis. And then another application is in plants, in water transport in plants. So if the water in the leaves, okay, if the water in the leaves evaporate, what happens is um, you have more water in the stem compared to the leaves. So water will move to the leaves, and then what happens is you now have more water in the roots compared to the stem. So the water will now go up from the roots to the stem and so on. So that is also osmosis. So remember, we have cells in your plants. So it's not like how water flows through a pipe. It's not like that. So your water overcomes some barriers like the cell walls, etc. So that's why it's osmosis. Also in fish, the principle of osmosis is taking place in fish, especially if we need to distinguish between seawater fish and freshwater fish. So you know that freshwater, we don't have um, salt dissolved in it. So we have fresh water, okay, versus seawater. So in seawater, we have salt. Okay, we have salt in seawater. In fresh water, we can consider it like pure water, and then of course in the blood of fish we have solutes dissolved in the blood, right? So the tendency would be for the fresh water to spontaneously undergo osmosis through the gills of freshwater fish, and that brings oxygen into the bloodstream of your fish. On the other hand, in seawater, we have salt, and usually the salt concentration is higher than the concentration of solute dissolved in the blood of fish. So it means that seawater cannot spontaneously undergo osmosis through the gills of the fish, of seawater fish. So actually, seawater fish directly drink the water, the seawater, so that they can have oxygen inside their bodies. And then they spontaneously excrete it out via the gills. Okay. Now, when we talk about osmosis, there are three terms that appear in the concept of osmosis. We have isotonic, hypotonic, and hypertonic. So this is applicable in cells in the body. So we compare the concentration of the solute inside the cell and outside the cell. So if the concentration of solutes is equal inside and outside, we say that the solution outside of the cell is isotonic. So there's no effect. We have an equal rate of osmosis from inside the cell to outside and from outside the cell to inside the cell. Then we have hypotonic. So when we say hypotonic, it means that the solution outside the cell has less concentration of solutes compared to the solution inside the cell, or basically the cytosol. So outside you have less concentration of solute, inside you have greater. So the flow of water, so the flow of osmosis will be from outside to inside the cell. And the effect is your cell will swell. So because water is flowing into it, so it swells, and sometimes if your cell doesn't have a cell wall, the cell will burst. So it will die. And then the third one, we have hypertonic. So if we say a solution is hypertonic, it means it has a greater concentration of solutes compared to the cytosol. So this means that the flow of osmosis will be from inside to outside the cell. So the cell is losing water. So that means the cell will decrease or will shrink. The size of the cell will decrease, so it will shrink. So that's the effect of a hypertonic solution. That is why your IV drips must have the same solute concentration as that of blood. So we have considered colligative properties of non-electrolytes. So the previous discussion, we considered colligative properties with non-electrolytes in mind. So recall that we know that electrolytes dissociate in solution. So actually the effect of electrolytes, if we talk about colligative properties, is we have greater value of colligative properties if we have electrolytes. So what I mean is that, for example, if we have 1 molar glucose, which is a non-electrolyte, and 1 molar sodium chloride, which is an electrolyte, and let's say the vapor pressure lowering for a 1 molar glucose solution. So there's a change in the pressure, right? So the pressure is lower. So the pressure, let's say, is 0.01 millimeters of mercury for a 1 molar glucose. The vapor pressure lowering for a 1 molar sodium chloride would be 0.02 millimeters mercury. So you see that it's double that of the glucose. Why? Because we've seen that sodium chloride dissociates into sodium and chloride ions. So in reality, we have a total of 2 particles for every unit of sodium chloride. So again, when we say 1 molar sodium chloride, what we actually have is 1 molar sodium and 1 molar chloride. So we have a total of 2 molar of ions.